Hello everyone, and welcome back to Dr. Liu's VCE Chemistry channel. Before we start, here is a brutal question. Which question caused over 70% of chemistry students to completely fail in the 2025 VCE exam? It's this exact voltage calculation right here. Official data shows a mere 29% of students scored marks, with the rest walking straight into a hidden alkaline pH trap. This is why top study scores slip away. You are just memorizing lines instead of establishing total command. In today's walkthrough, we'll use the iron rule of circuits and the water line boundary to dismantle these high-level questions. More importantly, I'll unlock a secret weapon schools rarely teach, the Linguistic Edge, to help you write flawless, full-mark Section B responses. Grab your data book, sharpen your focus, and let's get started. The rapid popularization of wearable electronics, soft robots and implanted medical devices has stimulated extensive research in flexible batteries, which are bendable, foldable, knittable, wearable, and/or stretchable. Different from the conventional batteries that utilize rigid and bulky electrodes, current collectors, metal anodes, liquid electrolytes, and packages, flexible batteries require the flexibility of each component to accommodate diverse shapes or sizes. Metal-air batteries are considered a suitable option for flexible batteries. Oxygen, O2, in the air reacts with a metal electrode in all cells. Sodium, Na, magnesium, milligram, aluminium, Ul, and zinc, Zn, are being investigated using polymer and gel electrolytes. A diagram of one of the cells in a flexible zinc-air battery is shown below. The iron rule of circuits. The keywords here are polymer or gel electrolyte, which constitutes the internal circuit. It is crucial not to confuse this with the external circuit. In an internal circuit, no electrons flow, only ions migrate. This iron rule is suitable for any battery, regardless of the type. A and C electrons, these are incorrect. Based on the rule above, electrons stay in the external circuit, the wires and device, they cannot float through the electrolyte. B. Metal ions flow from anode to cathode, this is correct. As zinc is oxidized at the anode, zinc ions are released into the internal circuit and migrate toward the cathode to balance the charge. D. Metal ions flow from cathode to anode, this is incorrect. Because it describes the opposite of the natural ionic migration required during discharge. To maximize voltage, you need the widest possible gap on the electrochemical series. This is determined by two competing variables. Key 1, the electrolyte, pH dictates the high point. The reduction of oxygen is the cathode reaction for all options, but its strength depends on the concentration of hydrogen ions. In acidic electrolytes, oxygen has a higher starting potential. In alkaline electrolytes, the potential of oxygen is significantly lower. Strategic rule: acidic environments provide a much higher ceiling for the EMF. Key 2, the metal activity, the low point. The anode must be an active metal with a very low, negative, reduction potential. Looking at the electrochemical series. Conclusion. Although sodium is the most active metal, its potential is wasted in an alkaline electrolyte. Because the oxygen potential drops by 0.83 V compared to acidic conditions. The combination of magnesium and acid, option A, creates the largest overall gap, providing the highest potential difference. Correct answer, A. To understand why certain batteries are more stable than others, we have to look at the competitive struggle for reaction that happens the moment moisture enters a cell. The hidden competition. In a metal-air battery, the metal anode is designed to react with oxygen. However, when moisture is present, a side reaction becomes possible. The metal may attempt to react with water instead. If the metal is aggressive enough, it will strip the hydrogen away from the water molecules to form hydrogen gas. This not only wastes the metal, but can also cause the battery to swell or fail. The water line on the series. The electrochemical series acts as a map of chemical strength. On this map, there is a specific boundary, a water line, which represents the point at which water is reduced. For a metal to react spontaneously with moisture, it must sit below this water line on the series. The active metals, sodium, magnesium, and aluminium, are all located deep in the lower section of the electrochemical series, well below the water line. Because they sit so low, they are extremely eager to give up electrons. To these metals, water is an easy target. The moment moisture is present, they will prioritize reacting with it, leading to the unwanted side reactions that degrade the cell. The stable exception. Zinc is the outlier in this group. On the electrochemical series, zinc sits above the water line. Even though it is active enough to react with oxygen, it is not strong enough as a reducing agent to force a reaction with water. The result. Because zinc is positioned above the threshold where water can be reduced, it is thermodynamically forbidden from reacting with moisture under standard conditions. While sodium, magnesium, and aluminium are effectively too active for their own good, constantly prone to corroding in damp environments, zinc remains calm and indifferent to moisture. This makes the side reactions less likely in the Zinc-air cell, explaining why zinc is the most reliable material for batteries that must function in the real world where humidity and moisture are unavoidable. The focus of question 11 is the fundamental design challenge of fuel cells: how to manage the interaction between gases, catalysts, and electrolytes. To maximize efficiency, we must look at the physical structure of the electrode itself. The triple phase boundary. In a fuel cell using gaseous reactants, like hydrogen and oxygen, the reaction can only occur where three things meet: the gas, the fuel, the catalyst, usually on the electrode surface, and the electrolyte, which carries the ions. This meeting point is known as the triple phase boundary. If an electrode is dense or solid, this boundary is limited to the very outer surface of the material, which creates a massive bottleneck for the reaction. Why porosity is the key? To significantly enhance efficiency, we incorporate porous electrodes. Maximizing surface area, a porous structure acts like a high-tech sponge. By having millions of tiny pores, the internal surface area of the electrode becomes thousands of times larger than its external dimensions. Facilitating diffusion, these pores allow the gaseous reactants to diffuse deep into the electrode, ensuring that almost every bit of embedded catalyst is put to work, rather than just the atoms on the outside. Evaluating the design features. The porous advantage, option C. By maximizing the surface area available for catalytic reactions, we increase the rate of reaction and the total current the cell can produce. This is the single most effective way to enhance efficiency. The diffusion limit, option A. Using a dense, non-porous electrode is the opposite of what is needed. It would choke the cell by limiting where the gas can actually react. The electrolyte trap, option B. While electrolytes are essential for transporting ions between electrodes, using them to transport the gaseous reactants themselves is inefficient, as gases dissolve poorly in liquids. The membrane role, option D. While an impermeable membrane is necessary to keep the fuel and oxygen from mixing dangerously, it is a safety and separation feature rather than the primary engine of efficiency. Conclusion. Efficiency in fuel cells is a game of surface area. The more porous the electrode, the more room there is for chemistry to happen. Correct answer, C. To calculate the mass of oxygen consumed, we must bridge the gap between electrical charge and chemical quantity using a logical three-step flow. From charge to electrons. Our first objective is to determine exactly how many electrons were moved to produce 36,000 C of charge. By using Faraday's constant, the exchange rate between electricity and chemistry, we find that this amount of charge is equivalent to approximately 0.373 moles of electrons. The stoichiometric ratio. Next, we turn to the chemistry of the cathode. In a hydrogen-oxygen fuel cell, every single molecule of oxygen, O2, requires exactly 4 electrons to be reduced into water. This 4-to-1 ratio is the bottleneck of the calculation. It means the amount of oxygen consumed is only 1/4 the amount of the electrons we just calculated, resulting in roughly 0.09325 moles of O2. The final conversion. Finally, we convert this chemical amount into a physical mass. Multiplying the moles of oxygen by its molar mass brings us to the final result. Approximately 2.98 g of oxygen gas was consumed to generate that specific charge. Correct answer, B. This question asks us to connect the structural innovation of the electrolyte-free fuel cell, EFFC, with a specific pillar of green chemistry, designed for energy efficiency. The innovation of the EFFC. In a conventional fuel cell, the sandwich of anode, electrolyte, and cathode creates multiple physical boundaries. Each time a charged particle, ion or electron, crosses from one material to another, it encounters resistance. In physics and chemistry, resistance invariably leads to energy being wasted as heat. Evaluating the claims. Claim I, superior conductive properties. By using a single porous layer made of highly conductive materials, the cell allows electrons and ions to move with much less effort. Reducing internal resistance is a direct way to ensure that more of the chemical energy is converted into useful electricity rather than being lost to the surroundings. This directly aligns with maximizing energy efficiency. Claim 2, fewer internal interfaces. Interfaces are the friction points of a battery. A conventional cell has 2 major interfaces, anode electrolyte and electrolyte cathode. The EFFC eliminates these distinct boundaries. Fewer interfaces mean fewer obstacles for the reacting species, resulting in less heat loss. Keeping energy within the system, as electrical output rather than heat, is a core tenet of designing for efficiency. The green chemistry connection. The principle of design for energy efficiency states that chemical processes should be designed to minimize energy consumption. In the context of a fuel cell, efficiency means getting the maximum electrical work out of every mole of fuel. Both the use of superior conductors and the removal of energy-sapping interfaces work together to achieve this goal. Correct answer, C. This presentation provides a comprehensive walkthrough of the 2025 VCE Chemistry Exam, specifically targeting the high-frequency area of electrochemistry, questions 7 to 9, 11, 12, and 17. By bridging rigorous chemical theory with real-world student performance data, the session identifies common pitfalls and reinforces the total command logic required for exam success. Full Battery Section 1. Flexible Metal Air Batteries, Q79. This segment explores the thermodynamic and mechanical boundaries of galvanic cells. The iron rule of circuits, reinforcing that in the internal circuit, ions, never electrons, carry the charge. The EMF or pH interplay, analyzing why magnesium in an acidic environment outperforms sodium in alkaline conditions, despite sodium's higher standalone activity. The waterline boundary, a narrative approach to the electrochemical series, explaining why zinc is the superior choice for moisture-prone environments due to its stable position relative to water reduction. High voltage sign section 2, fuel cell engineering and quantitative analysis, Q11, 12, 17. A focus on the design principles that separate theoretical chemistry from industrial efficiency. Triple phase boundaries. Why porosity is the non-negotiable feature for maximizing catalytic surface area. Stoichiometric precision. A breakdown of Faraday's law calculations, transitioning from coulombs to mass with a specific focus on the 4:1 electron to oxygen ratio. Innovative EFFC design, connecting green chemistry principles to the removal of internal interfaces to minimize heat loss. Key insights. The data reveals a significant spread in student mastery. While 80% of students understand the physical necessity of porous electrodes, only 29% successfully navigated the complex interaction between electrolyte pH and electrode potential. This summary emphasizes that electrochemical series mastery, understanding not just the list, but the environmental thresholds, is the unifying thread for top-tier performance. If you need my help, please add me on WeChat or WhatsApp and send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.